This is questions from Holder AAHL complex numbers. Right after we learned the concept of modulus argument form. So let's solve some examples here. Number 38. The expression in terms of trigonometric functions for argument of a plus bi. So generally, the argument of a plus bi can be found from arctangent, imaginary over real. But the problem is the range of arctangent is only from negative 2 over pi over 2 to pi over 2, which means we can have all type of complex numbers, quadrant 1, 2, 3, 4. But arctan gives the argument only for here because negative pi over 2 to pi over 2. So if we have any numbers on the quadrant 2 or 3, it doesn't cover for it. So in that case, we have the solution. When you find something and if you know the real part is negative, then simply you can add pi here. So this is the answer. I will show you some examples. For example, if you have 1 plus I and negative 1 minus I, so this is 1 comma 1 and this is negative 1 comma negative 1. So this is pi over 4. So argument of 1 plus I is pi over 4 from arctan, imaginary over real, like this. So this one still, argument of negative 1 minus I becomes from argument arctan, negative 1 over negative 1, which is 1. But this is not our argument because this gives you pi over 4 only. So as I suggest you, but we can add pi to here. So the real argument for this is 5 pi over 4. And let's go to number 38. I cis theta. When you perform the operation of the complex numbers, whatever it is, not only complex numbers, you should consider the form. So it should be consistent in terms of the form when you add, subtract, multiply or divide. So this one is multiplication. So now I and cis theta. Cis theta is polar. I is Cartesian. So we need to change something, but this is a multiplication. So maybe polar could be better. And also the last form will be polar. So let's go to polar. I, Cartesian, is 0,1, which has the modulus of 1 and argument of pi over 2. So I is cis pi over 2 times cis theta. So this simply, we can add the argument. So this is the answer of 39. Now for T. 1 plus I tangent theta. In modulus argument form. Okay. So modulus is 1, let's call it z. Z is 1 plus I tangent theta. So now I want to find the modulus of z is square root 1 squared plus tangent square root of theta, which is from the Pythagorean identity. This becomes secant squared of theta. And this can be, because this is squared in the square root, so this can be only secant theta. But just in case, secant theta can be the negative value. So let's put the modulus sign around the secant theta. and argument of z. As we saw the previous question, from the previous question, and this is the one which is positive real value, so we don't need to consider plus pi. So octant, imaginary part over real part. So this is arctan with tangent. So this becomes theta because those are like inverse function relations. So modulus argument from modulus is secant theta in the modulus sign and cis theta. Number 41, count example. So to find the count example, just we can try something. Count example is just it's better to find from the trial and errors, because there is no like a specific only one answer or something like that. So let me find something simple one. Let's say argument, let's say z1 will be 1, z2 I, let's say. Argument of z1 is 0. Argument of z2 is pi over 2. Because 1 is here, I is here. 1 plus I here, which means argument of 1 plus I is pi over 4. And argument of z1, so this is on left side is pi over 4. And right side is 0 plus pi over 2. So those are not consistent. So it is not, it is the count example. And let's go to number 42. So Z and W, multiplication and also division. So let Z be R1 cis theta 1, W R2 cis theta 2. ZW becomes R1 R2 cis theta 1 plus theta 2. This one 8 cis cos negative, so 3 pi over 4. And Z over W, R1 over R2 cis theta 1 minus theta 2 becomes 2 cis 1 over 2 cos pi over 3. So R1, R2 becomes 8. R1 over R2 is 2 R2. So 2 R2 becomes 8. So R2 becomes 2. Because for us, the modulus is only positive number. Can be 0 too, but anyway, not non-negative. R2, when R2 is 2, R1 becomes 4. And theta 1 plus theta 2 becomes 9 pi over 12. Theta 1 minus theta 2 becomes 4 pi over 12. When we add them together, theta 1 becomes 13 pi over 12, so 24. Theta 2 becomes 24, 18, so 5 pi over 24. So R1 for cis 13 pi over 24, 2 cis 5 pi over 24. Let's go to number 45. Sketch the curves. So described by, so Z modulus is 2. So modulus is 2, which means the distance from the origin 2. So the all possible case, all those points along this circle is possible. 2, 2, negative 2, negative 2. Argument of pi over 6, like this. Real imaginary number. And real part squared, let's say Z becomes x plus iy, then real part is x squared, imaginary part becomes y. Y equals x squared. So real imaginary number. Like this, the parabola. Oh, it should not go down there. Oops. Like this. Number 46. Z minus 5i 3. Let's say what is smallest possible value of z. Z again x plus iy. Then x x plus y minus 5i modulus x squared y minus 5 squared becomes 3. I think this is a little bit old question, like the questions from the old curriculum, because now we don't have these circle equations in our curriculum. But let's go anyway. This one had the center 0,5 and radius of 3. So this is the all possible points who satisfy this equation. So, but this is asking us about the possible z, which is the distance from the origin for this circle. So, but smallest one, which is closest from the circle. So this is closest. So because if we try to go further, all are like longer than the first suggestion. So this is the shortest. Since the radius was 3, this was 5, so the shortest one is 2. 47, proof. Let's go. This is, I guess, about trigonometry identity. 1 plus cos 2x plus I sine 2x over 1 minus cos 2x minus I sine 2x. So for the rationalization, 1 minus cos 2x plus I sine 2x. So again, same, 1 minus cos 2x plus I sine 2x. So the denominator, 1 minus cos 2x squared plus sine squared of 2x. The upper part, let me like expand and calculate at the same time. So when I do this, the real part, if I group them like this, then this is the product of sum and difference, which is the difference of squares. So 1 squared minus cos squared of 2x. And for the real part, we can find from here, minus sine squared of 2x plus I. Let's find the imaginary part. It has from here and here 1 plus cos 2x and 1 minus cos 2x. So cos 2x will be eliminated. So now we have 2 sine 2x. So actually this becomes 0 because sine squared over 2x plus cos squared over 2x equals 1. So now we have I 2. Let me go to, because this is just a single angle, but and now we have double angles. So let me go at the same time. Cos x below 1 minus 2 cos 2x plus cos squared over 2x and sine squared over 2x, again Pythagorean identity, which is 1. So let me put it like this. So this has 2. So now we don't need any more 2. So upper like numerator 2i sine 2x sine x cos x, and in denominator we still need to go to the single angle. So cos of 2x has three different formulas, but usually because since we have this one, we use the formulas to eliminate this one. So 1 minus 2 sine square root of x. So let's remove this one. Then 2 sine square root of x, 2i sine x cos x, 2 sine. So cos over sine, which is cotangent of x. And let's go to number 49. So here, let z be x plus iy. Then z square, modulus of z, x squared over y squared of in the square root plus x plus iy becomes 8 plus 4i. So now it's easy to find y equals 4. So square root x squared over 16 plus x could be 8. We cannot put x into the square root. If we have x here, let's say, we can put it in because this is multiplication. But plus or minus cannot come in like that way. So we need to go 8 minus x and square them on both sides. 64, 16x, x squared, 1, 4, 1, x is 3. So now we can tell the z is 3 plus 4i. And number 50, z and z minus I. Again, let z be x plus iy, x squared of y squared, x minus 1 squared plus y squared. So x squared y squared, x squared minus 2x plus 1 plus y squared. So x becomes 1 over 2. So real part is 1 over 2. But only this is the condition. Actually, it doesn't matter about y because this is the result is independent from y. So if we want to sketch the graph, the solutions, this one, then we can draw the graph here, which is real part of z is 1 over 2. That's it.